Hello, Prof. We are Team 2 and we will be presenting our project Biomechanical Gesture Recognition and Analysis, also known as BGRA. In the realm of healthcare, Internet of Things projects are changing the way we approach treatment and rehabilitation. One such innovative application is the BGRA system, designed specifically for aiding the upper limb motion rehabilitation of stroke patients. By harnessing the power of technology, this project aims to provide precise real-time feedback, enabling patients to perform effective physiotherapy exercises from the comfort of their homes. The BGRA employ a combination of these cutting-edge technologies. First is the M560 Plus microcontrollers, which serve as the backbone of the system, facilitating seamless data collection and processing. Secondly, MediaPipe's post-landmark library is used for accurate tracking and analysis of human body postures and movements. And lastly, edge computing. By processing data locally, edge computing significantly reduces latency, providing instant feedback, which is important for effective rehabilitation. BGRA focuses on enabling real-time feedback and monitoring for patients, aiming to enhance overall outcomes. Through the integration of advanced technologies, we seek to provide innovative solutions in healthcare. Our main objective is to provide real-time feedback to both patients and healthcare providers. This immediate communication allows for prompt adjustment and interventions, ensuring optimal care. We also aim to monitor patient data efficiently. By identifying any anomalies in real time, we can facilitate timely intervention, preventing potential complications. One of our main features is the ability to receive and analyze data in real time. This capability allows healthcare providers to intervene and adjust treatment plans as needed, ensuring the best possible care for patients. We utilize advanced algorithms such as convolutional neural networks for accurate gesture detection. This enhances accessibility and interaction, making it easier for patients to engage with their healthcare providers and receive the care they need. Our project provides patients with easier access to healthcare services. By reducing barriers to care, we aim to ensure that everyone can receive timely and effective treatment. We streamline healthcare processes through automation and real-time data analysis. This not only improves efficiency but also reduces the likelihood of human error.
For BGRA, we are utilizing cutting-edge technology to change physical rehabilitation. Our hardware components include the Raspberry Pi 400, which acts as the brain of our system, analyzing data and managing communication. We are using the Logitech C270 HD webcam to capture real-time motion data, essential for our gesture analysis. Additionally, the M560 Plus microcontroller is employed for its built-in sensors, providing crucial information on the device orientation and movement. On the software side, we have integrated several key technologies to power our system. At the heart of our gesture analysis is MediaPipe post-landmark detection, a powerful machine learning library. This tool employs convolutional neural networks, or CNNs, to precisely track human body postures and movements. CNNs are advanced algorithms renowned for the ability to recognize patterns and features in images, making them ideal for post-estimation. By analyzing video data, MediaPipe's post model can accurately identify key points on the human body in real time, enabling detailed analysis of the patient's movements during rehabilitation exercises. To ensure seamless communication between our devices, we are utilizing MQTT. This lightweight messaging protocol is tailored for small sensors and mobile devices, allowing for efficient data exchange and real-time feedback. Lastly, we rely on OpenCV, the renowned open-source computer vision library. OpenCV is crucial for processing and analyzing the video data captured by our webcam. It provides the tools we need to handle image manipulation, feature detection, and much more, supporting our system's ability to deliver accurate and timely feedback for our physical rehabilitation.
Let's dive into the physical setup and configuration of the BGRA. For initial connection, we start by connecting the Logitech C270 HD webcam and the M560 Plus to the Raspberry Pi. The webcam captures real-time video data, essential for our gesture analysis. Meanwhile, the M560 Plus, communicating via the MQTT, gathers additional sensor data. We then utilize the M560 Plus's built-in MPU6886 motion tracking sensor to detect motion. The data from these sensors is sent through MQTT under the topics IMU data D1 and IMU data D2 for processing. For the placement of the device, the webcam is strategically positioned to cover the patient's full range of motion during exercises. The M560 Plus is attached to the limb or body part under observation to ensure accurate data capture. For the MQTT setup, we've set up an MQTT broker within the Raspberry Pi 400 to facilitate message exchange between devices. The topics are organized to streamline data handling, while subscribers are set to receive data efficiently. Now onto the configuration of the system. For the software installation, we use OpenCV for video capture and processing, MediaPipe for pose estimation, NumPy for numerical operations, and SciPy to compute z-scores for sudden movement detection. For the network configuration of our prototype, The M560 Plus and Raspberry Pi are connected to a common network, such as a hotspot. This allows for local communication between the MQTT client server. Lastly, for the MQTT client initialization, we initialize an MQTT client with a unique identifier and connect it to the MQTT broker. The client subscribes to specific topics to receive sensor data and publishes messages to the flagged results topic when sudden movements or spikes are detected.
The BGRA works in three stages: data capture, data processing, and communication. Our system uses the Logitech C270 HD webcam to capture real-time video data, essential for gesture analysis. The M560 Plus, equipped with an MPU 6886 motion tracking sensor, captures accelerometer and gyroscope data, providing insights into the acceleration and orientation of the patient's limbs during rehabilitation exercises. In data preprocessing, we have three main processes: preprocessing, post-estimation, and gesture analysis. In preprocessing, we capture and mirror video frames, then convert them to RGB color space for MediaPipe's post model. We also prepare sensor data and set up rolling windows for spike detection. For post-estimation, we utilize MediaPipe's post-landmark detection to identify key body points. These landmarks are used to calculate angles between joints, such as the shoulder and the elbow, which are crucial for detecting sudden movements. In gesture analysis, we analyze movements and postures by calculating angles between joints. We can identify specific rehabilitation gestures. We also use rolling windows and z-scores to detect spikes in accelerometer and gyroscope data. These scores help us to identify significant deviations in the data, indicating potential sudden movements or spikes. Lastly, communication. We employ MQTT for communication between Raspberry Pi and M560 Plus. The system subscribes to topics to receive sensor data and publishes messages to alert healthcare professionals or provide patient feedback. Sensor data is transmitted via MQTT messages, and then the system provides visual feedback through the video feed and real-time data plots.
So to begin, we start running the main script that's merged with the BGRA and the M5 stick with MQTT. As you can see in the terminal, all the values received from the topic for the accelerometer and gyroscope values. Here's a graph where you can see both gyroscopes and accelerometer for both device 1 and device 2. Values coming in from MQTT topic is updated immediately on the graph. So any movement can be seen in the graph itself, from jerks to smooth raises of the arm. You can see as I move my hand, you can see a jerk. The BGRA and the MQTT for the plotting requires multiprocessing. As you can see from the video live feed, the landmarks are placed on the arm, and as I raise my arm, you can see it follows and tracks it. And similarly on the graphs itself, you can actually notice the curves and waves based on accelerometer and the gyroscopes based on location. Now you can see the values coming in for the elbow and the shoulder. The values are calculated based on angle, and the values are using z-score. So if any values within a certain window frame is over a certain threshold, will be flagged. And the next script we run is actually a subscriber to the flag topic. As you can see, as any sudden movement, a timestamp will be sent to the topic flagged race results, and nurses, the values can be seen on the topic itself. As you can see from the graphs and the flag system itself, that was a jerk. And then the topic is sent is a certain timestamp and shows that, oh, at this point there was a jerk or something to be looked at.
In conclusion, we have developed a comprehensive rehabilitation monitoring system that combines the power of the M560 Plus sensors and the Logitech C270 HD webcam to capture detailed motion data and video footage. Utilizing advanced technologies such as OpenCV and MediaPipe, we are able to accurately analyze and interpret the patient's movement during the rehabilitation exercises. Our system not only provides real-time feedback to the patients and healthcare providers, but also opens up the possibility for remote monitoring and personalized rehabilitation programs. By leveraging MQTT for efficient data exchange and potentially integrating with edge servers or IoT platforms, we ensure scalability and flexibility in the data processing and storage. As we move forward, we aim to refine our system by enhancing gesture recognition algorithms, improving user interface, and improving the adaptation of the system. Thank you.